Pain is not damage. That sounds wrong. Of course pain is damage. You touch something hot, you burn, you feel pain. You break a bone, you feel pain. The damage causes the pain. That's the whole point. Except it isn't. That picture is wrong in ways that change everything about how pain works. Soldiers in combat report severe, objectively measurable wounds, deep cuts, fractures, shrapnel injuries, and feel no pain at all during the engagement. Not numbed, not shock, but genuinely not painful in the moment. Athletes break bones mid-game and keep playing. And in the opposite direction, people with chronic pain, real, debilitating, life-altering pain, often have no detectable tissue damage anywhere. And then there's phantom limb pain. A person loses a leg, the leg is gone, and they feel excruciating pain in the foot that no longer exists. Not a memory of pain, actual, present, intense pain in a limb that isn't there. No tissue, no nerve endings in the missing limb, no damage, and unbearable pain. Pain is not a report from damaged tissue. Pain is a construction the brain makes, a decision, an output, not an input. And understanding why the brain makes that decision, and when it makes it wrong, requires going into the physics of ion channels, the electrochemistry of nerve impulses, the architecture of the spinal cord, and finally, a question that physics hasn't answered yet. The nervous system has specialized sensors for potentially harmful stimuli. They're called nociceptors, from the Latin nocere, to harm. And the first thing to understand about them is what they actually detect, not pain. Nociceptors don't detect pain. They detect physical and chemical conditions associated with potential tissue damage. Extreme mechanical pressure, extreme temperatures, chemical signals released by damaged or inflamed tissue. They're alarm sensors, not damage reports. The alarm going off doesn't mean the house is on fire. It means the conditions are right for a fire. There are several types. Mechanonociceptors respond to intense mechanical force, the kind of pressure or deformation that could crush or cut tissue. Thermonociceptors respond to temperatures at the extremes, both very hot and very cold. And polymodal nociceptors, the most abundant, respond to all three, mechanical, thermal, and chemical stimuli. They're the general-purpose threat detectors of the peripheral nervous system. All of them have a threshold, a minimum stimulus intensity below which they don't fire. Normal touch doesn't activate them. Normal warmth doesn't activate them. But that threshold isn't fixed. It changes. After tissue injury, the area releases a chemical soup, prostaglandins, bradykinin, histamine, substance P, that lowers the activation threshold of local nociceptors. They become easier to trigger. Stimuli that normally wouldn't cause pain now do. This is allodynia, pain from a normally non-painful stimulus. Touch a sunburned shoulder and it hurts. The sunburn lowered the threshold of the nociceptors in that skin. The light touch is no different from before. The nociceptors are just primed to respond to it. This sensitization is protective in the short term. It makes the injured area tender, encouraging you to protect it. And it becomes problematic when it doesn't turn off. When a nociceptor detects a harmful stimulus, it has to convert that physical event into something the nervous system can actually use. This conversion, from physical event to electrical signal, is called transduction, and the mechanism is ion channels. Nociceptor membranes are studded with protein channels that span the cell membrane. Different channels are sensitive to different stimuli. When activated, they open. Literally, they change physical conformation, creating a pore, and allows specific ions to flow through. Primarily sodium and calcium, which are at higher concentrations outside the cell than inside, rush in when the channel opens. The resting state of a neuron is electrically polarized. The inside of the cell is at roughly -70 millivolts relative to the outside. Positive ions flowing in raise that potential. If it rises to about negative 55 millivolts, the threshold, it triggers an action potential. An action potential is a self-propagating wave of electrical change. Once triggered at one point on the membrane, it spreads along the axon by a chain reaction. Voltage-gated sodium channels open in response to the rising potential, allowing more sodium in, raising the potential further, which opens more channels in the adjacent membrane segment. Each section of axon triggers the next. The wave propagates. This is not like electricity in a wire. It's not electrons flowing along a conductor. It's a biochemical chain reaction sustained by ion concentration gradients that were established by energy-consuming ion pumps. The physics of a nerve impulse is closer to a burning fuse than to a copper wire. One channel worth knowing by name, TRPV1, the vanilloid receptor. It's activated by temperatures above 43 degrees Celsius. It's also activated by acidic conditions, which is why damaged tissue, which becomes acidic, is painful. And it's activated by capsaicin, the compound in chili peppers. This is why spicy food feels hot. Not metaphorically hot, literally the same hot. Capsaicin binds to TRPV1 and opens it, exactly as thermal energy does. The receptor can't distinguish between the temperature has gone above 43 degrees Celsius and this molecule has docked to my binding site. Both events cause the channel to open. Both produce the same electrical signal. The brain receives the same message from both and interprets both as heat and pain. Chili peppers don't burn you. They convince your senses they're burning you. The physics of molecular binding is identical to the physics of temperature-induced activation, from the receptor's point of view. Once the nociceptor fires, the signal travels to the spinal cord along one of two types of fibers, and the distinction matters because it explains something about the structure of pain you felt your entire life. A-delta fibers are myelinated. Myelin is a fatty insulating sheath produced by glial cells wrapped around the axon that dramatically changes the electrical properties of the nerve fiber. By insulating most of the axon surface, myelin reduces the membrane capacitance and forces the action potential to jump between gaps in the sheath called nodes of Ranvier. This saltatory conduction is dramatically faster than continuous propagation. A-delta fibers conduct at 5 to 30 meters per second. They carry sharp, immediate, precisely localized pain, the initial moment of a cut or a burn. C fibers are unmyelinated. The action potential propagates continuously along the axon surface, limited by the membrane physics of ion channel dynamics and capacitance. Speed 0.5 to 2 meters per second. They carry dull, diffuse, burning, aching pain, the throbbing that follows the initial sharp sensation. When you stub your toe, the first sensation, immediate, sharp, precisely located, is A-delta fiber pain arriving at the spinal cord and brain quickly. Then, a moment later, the deeper ache begins, C fiber pain arriving at lower speed. Two temporal peaks. One injury, different fiber speeds. The difference in speed is an engineering solution to competing physical constraints. To conduct faster without myelination, a neuron needs a larger diameter axon. The conduction velocity scales roughly with the square root of axon diameter. A large enough unmyelinated axon to match A-delta speeds would be metabolically expensive and physically impractical at scale in a biological organism. Myelination achieves high conduction velocity without requiring large diameter, by changing the electrical geometry of the fiber. Physics applied to evolutionary biology. The pain signal arrives in the spinal cord at a region called the dorsal horn, and here something that changes everything about pain becomes clear. The signal is not simply relayed upward, it's processed, modulated, filtered. The first editorial decision in the pain system happens here, before the signal ever reaches the brain. In 1965, two researchers, Ronald Melzack and Wall, proposed what became one of the most influential ideas in pain science, the gate control theory. The dorsal horn acts as a gate. The gate can be more open or more closed, depending on the balance of signals arriving from different nerve fiber types. Here's the mechanism. Large diameter A-beta fibers carry normal, non-painful touch and pressure information. When they're active, when you're touching something normally, they activate inhibitory interneurons in the dorsal horn that reduce the transmission of signals from the small diameter pain fibers. The gate partially closes. Less nociceptive signal gets through to the brain. This is why rubbing an injured area provides relief. You're activating A-beta fibers with touch, which activates inhibitory interneurons, which closes the gate on the pain signal. You're using the physics of competing fiber inputs to modulate dorsal horn transmission. But the gate is also controlled from above. Descending pathways from the brain, from the periaqueductal gray, from the rostral ventromedial medulla, from the prefrontal cortex, send signals down to the dorsal horn that modulate the gate. These descending pathways carry the influences of attention, emotion, expectation, and context all the way down to the first relay station of pain processing. This is the physical mechanism by which your emotional state changes how much pain you feel. Not metaphorically, not just cognitively, but through actual neural pathways sending inhibitory or facilitatory signals to the dorsal horn, changing how much of the peripheral signal gets amplified or suppressed before it ever reaches the brain. When the signal reaches the brain, it doesn't go to one place. It goes to many places simultaneously, and each does something different with it. The thalamus receives the incoming signal and distributes it. The somatosensory cortex processes the sensory discriminative aspects, where the pain is, how intense it is, what it feels like physically. The anterior cingulate cortex processes the affective component, how unpleasant it is. The insula integrates bodily state and emotional significance. The amygdala contributes emotional context. The prefrontal cortex brings in expectation, memory, and meaning. The distinction between somatosensory cortex and anterior cingulate cortex is not trivial. These can be dissociated. There are clinical cases, patients with damage to specific brain regions, and controlled studies using hypnosis, where people report pain that is fully perceived in terms of its sensory qualities but doesn't bother them. They can tell you exactly where it is and how intense it feels, but the suffering is absent, the unpleasantness is gone. What we call pain in ordinary language is actually at least two things: a sensory event and an affective event. You can have the sensory event without the affective event. You can also have the affective event, distress, suffering, without a clear sensory source. These are separable in the brain's architecture. The placebo and nocebo effects are not about fooling weak minds. They're about the physical reality of expectation-driven neurochemistry. In controlled studies, subjects told a treatment will be painful report more pain from identical stimuli than subjects told it will be mild, with measurable differences in neural activation patterns. People given inert saline injections, described as powerful opioids, release endogenous opioids in the brain, actual measurable opioid activity, confirmed by the fact that the placebo effect can be blocked by opioid antagonists. Expectation changes the neurochemical state of the system. The brain is not a passive processor of incoming signals. It's a predictive system that sets up its own chemical state based on what it anticipates, and then processes the incoming signal through that state. Acute pain makes functional sense. It alerts you to damage. It motivates withdrawal and protection. It is, in the language of evolutionary biology, adaptive. The system works. Chronic pain is something different and considerably more interesting from a neuroscience perspective. In chronic pain, the system is generating pain that doesn't correlate with ongoing tissue damage. The alarm is running without a fire. The mechanism is central sensitization. After prolonged or intense nociceptive input, the synapses in the dorsal horn, the connections between the incoming pain fibers and the relay neurons, undergo strengthening. The technical term is long-term potentiation. The same synaptic strengthening mechanism that underlies learning and memory operates here. The synaptic connections become more efficient. The relay neurons fire more easily, more intensely, for longer, and in response to smaller inputs. The volume is turned up at the neural level, and the system that modulates it, the descending inhibitory pathways, the internal opioid system, is often dysregulated in parallel. In fibromyalgia, complex regional pain syndrome, and many forms of chronic back pain, functional imaging shows that the brain and spinal cord pain processing network is genuinely in a different state. Not imagining the pain, not malingering, operating in a sensitized, amplified mode where normal inputs produce pathological outputs. Chronic pain is the nervous system having learned to be in pain. The same neuroplasticity that lets you learn a language or a musical skill has, in response to prolonged nociceptive experience, reconfigured the pain system toward a state that perpetuates pain independently of peripheral input. And this reframes treatment. If chronic pain is a property of the nervous system's learned state, not of peripheral tissue damage, then fixing the periphery often doesn't fix the pain. Because the periphery isn't the problem anymore. The system learned something, and the learning doesn't automatically unlearn when the original cause is removed. Here's where I have to be honest about what the physics explains and what it doesn't. We can trace the complete chain: nociceptor activation through ion channel opening, transduction, action potential generation at threshold, signal propagation along A delta and C fibers at calculable speeds determined by myelin physics and axon geometry, dorsal horn gating modulated by competing fiber inputs and descending pathways, thalamic relay, multi-regional cortical processing, somatosensory, cingulate, insular, frontal, endogenous opioid release modulated by expectation and context, synaptic plasticity producing central sensitization. Every step in that chain has a physical mechanism. Every step is measurable. Every step is, in principle, describable by equations. What none of this explains is why any of it is accompanied by an experience. Why the electrochemical events in the anterior cingulate cortex are accompanied by suffering. Why the processing of nociceptive signals in the insula produces something that feels like something, the specific, irreducible, private quality of what pain is like. Why there is a felt experience at all, rather than just a physical system producing protective behavior in the dark, with no one home to feel it. This is the hard problem of consciousness, and pain makes it sharp. Because pain is phenomenologically among the most vivid things there is. The gap between the physical description, ion concentrations, membrane potentials, synaptic weights, receptor activation, and the phenomenal reality of what pain feels like from the inside is as stark as it gets. Adding more physical detail doesn't close that gap. It restates it at higher resolution. A more precise description of which neurons fire in which sequence during pain doesn't explain why firing neurons produce experience. It just describes the firing in greater detail. Dirac believed that when physical description is complete, It will be beautiful and consistent. The neuroscience of pain is genuinely, impressively detailed. The mechanisms are understood at a level of resolution that would have seemed impossible 50 years ago. But the question of why the mechanism produces experience, why there's something it's like to be in pain, has not been touched by any addition to the physical description. Pain is the most intimate physical event you have, entirely yours. Nobody else can feel your pain, not metaphorically, but literally by the physical structure of how pain works. It is produced by the same physics that describes any electrochemical system. And how a universal physics produces a private, irreducibly subjective experience, that is not a question the neuroscience of pain answers. It's the question the neuroscience of pain keeps pointing toward, more precisely, from every direction, as the mechanisms become clearer.